Alright, so this is my physics project, work, power, and energy. Okay, so what I did for my project is recreate a real life situation of a scene of kickball. Alright, so as you can see, my brother pitches me a ball, I kick it in the air, he gets it off the ground, and we both run to first base. Alright, now going back to the slideshow. So basically, here are some bar charts of these scenes that just happened, but just going more in depth. So basically, this first one on the left right here, it's a bar chart of the ball when it's pitched and when it's kicked by me. So in the system, we have me, the ball, the earth, my brother, and the ground. And as you can see on this first bar on the left, we have EK, EG, and EEL. So EK is kinetic energy, and this is energy stored in motion. EG is gravitational potential energy, and this is energy stored in objects that are above the surface of the earth or just like above the ground. And EEL is elastic energy, which is energy that is stored in things that can compress, like sort of like springs and like slinkies. All right, so as you can see on the left one, I put all 4 EK because when the ball is pitched to me, it's flat on the ground, but there is motion. So the only type of energy right there, or the only store of energy right there, is kinetic energy. And now moving on to the right side, when I kick the ball goes in the air, causing it to gain EG as well as EK because it's also in motion. So I just put half and half for that one. And as you can see, there's no E elastic or E dis, and E dis is just dissipated energy, which is energy that dissipates when one energy store transfers to another. But we're not gonna consider that, even though there is actually E dis. We're just gonna call this a frictionless world. Yeah. All right. So basically, our equation at the bottom right here. All right. So then we have EKA equals EKB plus EKG. All right. Moving on to the bar chart on the right, we have a bar chart of the ball fielded and ran to first. So in this one, as you can see, my brother is outside of the system, but what's in the system is me, the ball, earth, and the ground. All right, so on the first one, we have 3/4 EK and then 1/4 EG. And we have this because when the ball is essentially kicked in the air and hits the ground, it does bounce a little, so we're gonna count for the fact there's a little EG, but it's mostly in motion, so that's why we put majority EK. And then right, we have nothing because even though my brother picks it up and runs to first base with it, he is not in the system. So when we go down to our equation, we put EKA plus EGA equals 0 plus work done. And then I put in like little I put by brother, so work done by brother. All right, so bar charts for my brother and I did this for me specifically, but since we basically do the same thing, these are essentially my brother's bar chart too for what he does. So basically in the system we have the earth, the ground, me, and the ball. As you can see, there's no energy stores of any kind in the first because we're both motionless. I mean, he's standing there pitching and I'm standing there ready to kick. Both motionless. And then basically he pitches the ball, I kick it, we both run to get the ball and run to first base. So all of us have EK. We never really leave the ground, nor do we have elastic energy, nor really dissipate energy. We're not counting that. And so, yeah, so we have 4 bars EK, and then our equation really is just 0 equals EKB. And while this is for me, this applies for him as well. All right, now going on to work. So as we know, work equals force times distance. And as we know, work is measured in joules, force in newtons, and distance in meters. So for this first one on the left, we have the work done when hitting the ball. So my mass is 54.4 kilograms, which is approximately 533.12 newtons. And the distance I ran up to go kick the ball was 1.5 meters. So to find that, work equals 533.12 newtons times 1.5 meters. And you get an ultimate work done of 799.68 joules. Okay, so now moving on to the right. So we have running to first. So this is the work done I do running to first base. So my mass, or sorry, my force is the same. So it's still 533.12 newtons. But the distance I go is 2 meters instead of 1.5. So we do the same thing and we multiply by 2 meters this time instead. And we get a work done of 1066.24 joules. Alright, so more work done. So now we're doing work done against gravity by the ball. Because remember, when I kick the ball, it lands on the ground, my brother picks it up, causing it to do work done against gravity, or work against gravity, which is mgh, mass times gravity times height. So the mass of the ball is 1.5 kilograms. The gravity is always 9.8 meters per second squared. And height, how far high I picked it up was 1.25 meters. And so then multiply those together, 1.5 kilograms times 9.8 meters per second times 1.25 meters. And this equation and normal work equation, force times distance, is essentially the same, because when you multiply your mass by your gravity, you just get newtons, and newtons are measured in, or force is measured in newtons, and then you have your distance, and yeah. So then we get an ultimate work of 18.35 joules. Work done against gravity. All right, now finally moving on to this last one, we have how much work my brother does when running to first base with the ball. So his mass right now is 49.9 kilograms. Multiply that by gravity, and we get a force of 489.02 newtons. The distance he runs to first base is 1.75 meters. And we multiply those together, we get 855.785 joules. All right, finally, power. So power is essentially the rate at which work is done, and power, the equation for power, is work done over time. And in this, we're going to compare the work, or the power by my brother versus me, and see which one's greater. So as you can see on the left right here, his work done when he's running to first base is 855.785 joules, and the time it takes him is 3.25 seconds. Divide 855.785 joules by 3.25 seconds, you get a power of 263.3 watts. And remember, power is measured in watts, not joules. All right, so then on the right, we have me. So my work is 1066.24 joules, and the time it takes me to run to first base is 3.15 seconds. Divide those two together, we get, or my ultimate power is 338.5 watts. So as you can see, I ultimately generate more power than him, because it ultimately takes me, even though I may have more work done, I ultimately have a less time. It takes me less time to get the first, which, yeah. And yeah, that's basically it. So yeah, thank you.